Hello, universe. Today we will be talking about the Gauss-Green theorem. This theorem is one of the most beautiful theorems that I have learned in recent time. And I like to think of the Gauss-Green theorem as a philosophical lesson about life and balance. This theorem essentially tells us that internal effects tend to cancel themselves out on a large scale. Or at least we can observe the net internal effects of a system by only looking at its behavior on the boundary. And so somehow, to me, philosophically, this theorem speaks to the balance of the universe. But this is not a philosophy class, so let me just stick to the math here, and let's look at this theorem. So we're assuming that we have a bounded open set, subset of Rn, okay? And our boundary is C1. This means that locally our boundary is after some rotation, perhaps, and some translation, locally our boundary looks like the graph of a differentiable function. So anything that you kind of picture as, an open set with some sort of smooth boundary, or at least a differentiable boundary, that's what we're requiring by saying that the boundary of U is C1, okay? This means differentiable and the first derivative is continuous, okay? All right, so our theorem, we assume that we have a function small u belonging to C1 of the closure U bar, okay? So essentially we have a function which is defined on our set U and the boundary of our set. And this function maps the set U and its boundary into the real numbers. And it's furthermore, we're requiring that it is continuous and in fact differentiable with continuous derivative, okay? Okay, and under these assumptions, then since we're assuming U, this lower script U to be differentiable, we can take the partial derivatives with respect to the ith coordinate. And our theorem states that if we integrate the partial derivative of the function U with respect to the ith coordinate in x over our entire open set, and this is equal to the integral over the boundary of our set of the value of the function U on the boundary multiplied by the ith component of the outward normal vector to the boundary, okay? So picture the boundary, and then this kind of, this script V here, I'm not sure the exact correct terminology for this lettering, but just take it to be a script V. It's denoting the outward normal vector to the boundary of my set U. So if I picture the boundary in maybe three-dimensional space, let's say, for visualization, I picture my set in three-dimensional space. The boundary is some surface, and at each point on the surface, this nu encodes the outward normal vector. So the vector that's orthogonal to the tangent plane to the surface at every point. Okay, and I'll draw a picture of this in a minute so you can understand a little bit more of the geometry here. Okay. Now, part 2 of our theorem states that for a vector field U hat, which is a continuously differentiable map from our open set and its boundary into Rn, so think about every point in our open set, capital U, and its boundary, we attach a vector belonging to Rn, and this assignment of a vector field, these vectors change in a continuously differentiable manner. Okay, then the theorem states that the divergence of this vector field integrated over our entire set capital U is equal to the integral over the boundary of our set U of the projection of the vector field onto the outward unit normal vector direction of our boundary of our surface. Okay, so if I look at the amount of charge created in physics terminology, the amount of internal charge or field lines created within my open set U, this is going to be equal to the net flux of electric field lines outside of the boundary. So this has immediate consequences in physics and electromagnetism in particular, among other fields. But we can also just think of this mathematically as a statement about the divergence of a vector field and how it actually, the internal properties of the divergence of a vector field relate to the net flux outside of our surface. And recall that the flux outside of the surface is the projection of the vector field onto the outward normal direction. So if I have a surface here, and let's say that this is a part of my surface, okay, so U is going to be, it has to be a closed surface by our definitions of partial U, okay? Partial U is the boundary of the set. And so this surface, on its boundary, I have this normal vector field that is outward, so the outward pointing normal vector field. And the idea is that if I look at the projection of my vector field U onto this outward unit normal direction, I end up with an expression that is equal to the, if I integrate this over the entire boundary, this is equal to the integral over the open set U of the divergence of our vector field. Okay? Now, parts 1 and 2 of the theorem are equivalent, and so we only need to prove part 1, and part 2 will immediately follow. And let me just show you why. So, if I unpack this definition, and by the way, this nu here should be a vector, right? This is the outward unit normal vector to our surface partial U, or the boundary of U. Okay, so let's unpack the definition of the divergence. So we know that the divergence of the vector field U is just our gradient vector dotted with U, okay? And so if I dot the gradient with the vector field U, by definition, this is going to be the summation. I'm going to bring the summation outside the integral from I equals 1 to n, let's say, of the ith component of U, and then I'm going to take the xith partial derivative, okay? All right, so that's the gradient dotted with the vector field U. And then this dot product is going to be this, this same summation from I equals 1 to n, say, and now it's going to be the ith component of U multiplied by the ith component of the unit outward normal vector to the boundary of U. And so notice that if I just replace U with this ith coordinate function, ui, which by assumption of our vector field, our assumption on our vector field being C1 is equivalent to assuming that all of its component functions are just C1 functions from U closure into the real numbers. And so I can basically plug in this ui here into the formula for part 1 if I know part 1 is true, and then I get that these sums from I equals 1 to n, these sums are equal. Every term of the sum is equal. So the overall sum must be equal, okay? So part 2 follows as a direct result of part 1. And then if you know part 2, then you can actually recover part 1 just by choosing the right vector field, okay? So if you just choose a vector field that, that I think it just needs to be 0 in all of its coordinates except for one coordinate, then if you choose a vector field which is 0 in all coordinates except for one coordinate, then these sums here are just going to spit out a single term, and that single term is precisely the statement of part 1, okay? So part 1 and 2 are clearly equivalent, and therefore we only need to prove part 1 or part 2, okay? And then we'll automatically have established both results, okay? All right, so let me just rewrite it here. That the integral over the set U of the divergence of our vector field dx is going to be equal to the integral over the boundary of U of the projection of U onto the unit outward normal direction integrated against the surface element S. Now let me just quickly comment about this ds showing up here. So ds, as we'll see in the proof, ds is the surface area element of this surface partial U, okay? So picture a surface maybe in 3-dimensional space, although this is for Rn, so it could be in larger dimensions or smaller, but a surface in R3, let's say, then the idea is that this surface is going to have some area element, okay, ds, okay, and depending on the coordinates that we choose for our surface, that's going to influence what our area element is, but you can essentially think of the equations defining this surface are going to induce a natural area element, okay? And that natural area element is going to come from the Euclidean structure of the ambient Rn space. So just as a quick example of what ds might look like, let's just look at the sphere, okay? Then we actually know that that the area element of the sphere in R3, okay, if I have polar coordinates, let's say polar coordinates theta, phi, and r, where r is my radius. Let me just, because I'm going to use the physics convention for my coordinate system. So I want theta to be this angle, the angle that I make with the z-axis, r to be my radius, and then phi to be, I believe it's called the azimuthal angle. Theta is my polar angle here. Then we know from calculus 3 that this area element is going to be r squared sine theta d theta d phi, okay? And the way you derive this equation for the area element ds depends on the coordinate system that you're using, and it depends on the equations for your surface, okay? So our assumption that our surface has a boundary that's C1 means that we're going to be able to express the boundary locally via some function, some differentiable function, which relates to our coordinates, okay? And once we have this definition of the function for our surface, then we'll actually see in the proof exactly what this ds area element is, okay? All right, so we'll go into this more when we actually do the proof, okay? All right, now finally, before we get into the proof here, I also wanted to mention some corollaries, okay? So these are a whole list of corollaries. So if we have two functions which we are assuming are twice continuously differentiable functions from U closure into the real numbers, their output is in the real numbers. If I just write C2 of U it's assumed that u bar is the domain and the codomain is the real numbers, okay? Then the first formula is the integration by parts formula. In fact, for this first formula, we only need an assumption that these functions are C1. Then I have that if I take f, the partial derivative of f with respect to xi, multiply that by g, and integrate over u, I can basically transfer this partial derivative with respect to xi onto g. It'll cost me a minus sign, and then I have to add a boundary term, which is the integral over the boundary of u of f times g multiplied by the ith component of the unit outward normal vector, and then integrated over this surface boundary of u, okay? And this is a direct corollary of part one, namely, if you just look at the function fg and plug in fg for u here, then fg for u, if I take the xi partial derivative of fg, this is just f xig plus fgxi. This is the product rule from one-dimensional calculus. And then applying this product rule and just plugging that into this formula for part one, you immediately get this integration by parts formula, which is so pivotal for so many of these calculations in all of math. Now, we also get these three formulas called Green's formulae, whatever. So these three formulas are Green's formula, and let me just write that here. This is why I've written these corollaries in green here. So G1 through G3 are called Green's formula. Plural. Okay? And these are, again, pivotal in so many critical calculations. What we're going to see is we're going to try and cover the wave equation in n dimensions shortly. And when we talk about the wave equation in n dimensions, these formulas, in fact, all of this lecture will be pivotal in all of the calculations, okay? So why do these follow as a direct corollary? Well, if I just look at this this Laplacian here, so Laplacian of f is defined to be the divergence of the gradient of f, okay? This is the definition of the Laplacian. And so I can just apply this divergence theorem here. And if I apply the divergence theorem, then I get that the integrand, so that this left-hand side is just the divergence of gradient of f. The right-hand side is going to be just going to be gradient of f dotted with this outward normal vector v, okay? Gradient of f dotted with the outward normal vector. Well, this is just the directional derivative of f in the direction of the unit normal vector, right? Because this is a unit, remember, this is a unit normal vector to the surface, the boundary of our set, then essentially, since it's a unit vector, this encodes the directional derivative of f in the direction of nu. So that's precisely G1 here. So it's a direct result of part 2 of this theorem. And then if I look at G2, G2 is another useful formula. And here, I now can just view df.dg, okay? So this derivative operator, well, this is just the gradient, okay? So it's a little bit of confusing notation, but I guess the notation in the book that I'm using, which is Evan's PDE book, let me just show you real quick. The book that we're using is Partial Differential Equations, 2nd edition by Lawrence C. Evans, okay? And so he uses this capital D. One might equivalently just use the gradient, this gradient notation, which is what I'm more familiar with probably because of my physics classes, right? So so the idea is that I can write this as, gradient of f dot gradient of g plus this, this term on the right-hand side, so f Laplacian of g, which is del dot grad g. So these two terms, I can write them as, via the product rule, I can write this as just the divergence of f times grad g, okay? So the reason why this holds is because essentially for the divergence we have, if we expanded this in terms of its definition of the coordinate-wise derivatives, we could apply the product rule in each coordinate. This is a great exercise if you haven't done this exercise. You can apply the product rule in each coordinate, and then you're going to get that, basically you take the derivative of f, which is the gradient of f, you dot that into the vector field gradient of g, and so that's the derivative of the first times the second, and then you add the first argument times the derivative of the second, so f times the divergence of gradient g. Okay, so essentially these two terms of g2 can just be written as the divergence of the vector field f grad g, and then I just apply this this part 2 again here, and so I can take away the divergence operator and I just get f grad g dotted with the nu here. And then again, so f grad g dotted with nu. Okay, so f is a scalar function, and then grad g dotted with nu is again the directional derivative of g in the direction of the unit outward normal vector. So that's exactly this partial g over partial nu here, okay? All right, and so this is again just a direct corollary of part 2 of our theorem. And then the third green formula is actually just a result of the second Green's formula. Because of the left-hand side of this second formula is symmetric with respect to f and g, I can interchange the roles of f and g in g2, so I can also write df dot dg, this integral over u, x is the integral of g Laplacian f dx plus the integral of g, so the directional derivative of f with respect to the outward normal direction, ds, and this is over partial u, this is over u. And then, so these two equations, this is just interchanging the roles of f and g here, because this formula left-hand side is symmetric with respect to f and g, okay? And then I can subtract these two equations. When I subtract these two equations, I get g3, this formula g3, okay? All right, so basically what I briefly covered here, and you can verify these computations on your own if you want a good exercise, is that all of these critical calculational tools, okay, are direct corollaries of a single theorem, the Gauss-Green theorem. So we can see already that this Gauss-Green theorem is just so powerful, okay? And the proof is a little bit technical, and we're going to go through every step, hopefully in sufficient detail, okay? So my references for this video are, again, Appendix C of this textbook, Partial Differential Equations by Lawrence C. Evans, 2nd edition. So Appendix C has all these formulas. And then also I used Wikipedia's page, Wikipedia regarding the proof of this theorem to get kind of a proof. So Evans' book doesn't actually prove these theorems, it just states them. All right, so let's go ahead and jump into the proof. Since our boundary of our set is C1, this means that for every point P, let's say, belonging to this boundary, there exists an open neighborhood of P So let's say an open set W which contains P such that W is open in Rn, such that if I look at U intersect W, this is going to be the set of x1 through xn, which belong to the set W, such that xn is strictly less than some function g of x1 through xn minus 1, where g is a function from Rn minus 1 into R is continuously differentiable in all of its coordinates, okay? And the picture is that we have some large set U, let's say, okay? And then we've sort of zoomed in to a single point P on the boundary. So this is my set U. Here's the boundary of U. We've fixed a point P on the boundary. And then we've just kind of found some open set, say W, where I can view the boundary of U as a graph of a continuously differentiable function G, okay? So this slice of the boundary here is the graph of G, okay? And this is essentially what it means for the boundary to be C1, okay? All right, so we have this definition, and it's a local definition, but one thing we do know about the set U is that it is a bounded open set of Rn, and so its closure is compact, right? U union its boundary is compact, because compact sets in Rn are just closed and bounded sets, okay? So using this definition, we have an open cover, and this open cover is going to be U union with the union over P in the boundary of U of these WPs that I defined previously, okay? And this is an open cover of the closure of U. The closure of U is U union its boundary, okay? And this is a compact set. So this is compact in Rn, since it's closed and bounded by our assumption that U is bounded. And therefore, by compactness, we get a finite subcover. Okay, and so our finite subcover is going to be U union with, let's say, the union from, let me not use I, let's use K is equal to 1 to, let's say, R of these WPKs. Okay? And this is a finite subcover of U closure. Okay, and so we've now achieved a finite subcover of U closure. Let's draw a picture of where we're at. The picture is we have some set U in Rn. Now I've drawn the boundary of U here, and U is the inside of this set. And then U closure is the entire set union its boundary. For each point on the boundary, we've found some open set WP such that the boundary of U restricted to this open set WP is the graph of a C1 function. Okay, so you have something like this where we have a finite set of points pk, so here's p1 all the way through pk, and then we have these wpk's, and the wpk's are open neighborhoods of the pk's, and we know that the boundary of U is the graph of some continuously differentiable function when it's restricted just to this local open neighborhood. And then notice that all of these sets together, when I add them, all of these sets cover the boundary of U. And so if I union them with, so basically if I take U and then I union this, this set K is equal to 1 to R WPKs, this covers the boundary of U essentially. And so we get that this entire construction is an open cover of U closure. Okay, so this is just visually speaking what we've achieved so far, all right? Okay, and now what we're gonna do is we're going to actually restrict the proof to each of these open sets. We're gonna consider all of the open sets independently of each other. Now that might seem like a bit of a crazy jump. The reason why we're allowed to do this is because of the existence of something called a partition of unity, okay? So we know that there exists a partition of unity let's say phi k, where k is going to run from 0 to r, subordinate to this open cover. Okay, so what does this mean? For those of you who haven't learned manifolds or haven't seen partitions of unity, an extremely powerful tool for gluing together local properties to understand global properties on a manifold, okay? Here we're just working in Rn, so you don't need to worry about manifolds. But what is a partition of unity? Well, it's all these functions, and essentially each function satisfies the two properties that first, we require that the support of these phi k's are contained in the open set. So let's say WPK for k greater than or equal to 1. And just by my indexing here, support of phi 0 is contained in U, okay? So essentially, recall that the support function support of phi k, let's say, this is defined to be the set of points where phi k is not equal to 0, closure, okay? So I look at all the points where phi k is not 0, and I take its closure, and that's its support, okay? So what this is saying is that everywhere outside of these open sets, the phi k's are 0, okay? So for each open set, let's say U here, I've attached a function, and this function, so let's say this is phi 0 for U, and then let's say for WP1 here, I have a different function, phi 1, and the idea is that, and I'm drawing the graphs of these functions, that outside of the set U, these functions are 0. So that's what this first condition is saying, is that these functions are 0 outside of the corresponding set, okay? So if I pick a phi k, it's going to be 0 outside of WPK, or in the case of phi 0, it's going to be identically equal to 0 outside of the set U. And then the second condition we require for a partition of unity, and I'm going to draw this, I'm going to write the second condition up here, is that the summation of these phi k's, where k runs from 0 to r, is identically constant 1, okay? This is the key, okay? Is that all of these functions, when you add them together, they sum to 1, identically, okay? And so you could think of them as a bunch of bump functions. So if I have I have a bunch of open sets. On each open set, I have a bump function, okay? And that bump function is kind of looks like this, and it's 0 outside of the open sets. But then when I add all those bump functions together, I just always get 1 no matter where I am, okay? So let's try to draw this. It's going to be hard to draw, but let's try to draw it. So if I'm visualizing, now I'm visualizing an R2, okay? So I'm visualizing our construction that we currently have in R2. Here's the plane. And then essentially, each of these WPKs has an associated bump function. So let's draw those here, here, here. Maybe this is phi 1, phi 2, etc. Here's phi r. And then I have a bump function on the set U. So I have another bump function, phi 0 on U. And the idea is that they all might look kind of strange when you just isolate each bump function. It could have, it's going to be a smooth function. It's infinitely differentiable, but it could have any number of properties outside of the fact that it's 0 outside of my open set. However, when I add all these bumps together, when I sum them all together, I get the constant function 1. So I just get a function who at every point has height 1. It's just a constant function 1, okay? So we can see that essentially these phi k's provide us the ability to glue together local properties. So if we can prove this theorem, this theorem locally, like say we prove it on each of these open sets and we prove it on U, then the partition of unity will essentially allow us to glue together our local proofs to create a global proof of this theorem. Because this partition of unity sums to 1 everywhere, then I can write this integral of the xi derivative of u. I can just write this as 1 times, I can insert a 1 basically, 1 times uxi dx. And then I can insert a 1 as well on the boundary of u. Okay, so inserting the sum of my bump functions in for the 1 here, I can write this as the integral over u of the sum of the phi k's times u, and then I take the xi partial derivative. Notice I've just brought the 1 inside the xi partial derivative. That's totally okay because this is just the constant 1. So I can essentially manipulate this sum of the functions of the partition of unity like the number 1. So it certainly can be brought inside of a partial derivative since it's a constant. And then the idea is that the partial derivative with respect to xi, this is a linear operator, so the sum can be pulled out of the derivative, right? If I take the derivative of a sum, then I can just take the derivative of each term of that sum. Okay, so the sum can be pulled out of the partial derivatives, and I get the sum from k equals 0 to r, integral over u, of phi k u xi is equal to the integral over partial u of, or let's put the sum on the outside, sum from k equals 0 to r, integral over partial u. Okay, and then notice that pulling the sum outside of the integral is totally acceptable because all of these bump functions, these phi k's, are compactly supported, okay? So by the continuity of u, I know that this integral is well defined, and so I can just pull the sum. It's a finite sum, and I can pull it outside of the integral. This is why we needed the compactness assumption. When we used compactness, this gave us a finite sum. And so at this stage of the proof, we're able to pull the finite sum out of the integral with no questions asked, essentially. And that, again, is the compactness assumption was critical there. Now, if you didn't assume compactness, if you had an open set that was not bounded, you need to be more careful, and you'd need to ensure that this step of the proof, it could still work, but you'd need an additional integrability assumption on your function u in order to make this work. But since we've assumed compactness, we're totally good at this stage. Okay, so now look at this this expression. Well, this function is just a C1 function, okay? And this is a C1 function, and it actually is a C1 function with support. So this is a C1 of u bar, let's say, but it's supported in either u if k is equal to 0, or our WPKs if k is greater than or equal to 1, okay? That's because the phi k is the bump function is 0 outside of these sets, and so this function is only non-zero inside of these respective sets here. And I now just identify this phi k u function, and if I prove the theorem for this function phi k u, then it's, by this analysis here, it's going to be equivalent to proving the theorem globally, okay? So that means that I just need to go through each of these cases, these two cases here, and prove the theorem for functions that are supported in these respective sets. So I can assume additional information that my function is 0 outside of these sets, okay? So thus, the first case is that the support of u, I'm going to drop the phi k's now because I'm just replacing phi k u in my previous line with just u, okay, to make the notation simpler. So I can first assume that support of u is contained in the open set u, so it basically vanishes at the boundary. And the second is that support of u is contained in one of these WPKs, okay? If we prove the theorem for these two cases, then we can use the partition of unity to glue together our results by the previous analysis I showed on the board, and then conclude the theorem holds globally. So case 1 is if support of u is contained in u, okay? So the idea is that since the support of u is contained in the open set u, I can extend u to a function which is basically 0 outside of its support, okay? So I essentially extend u as follows to a function, let's say u twiddle from Rn into R, and we're going to set u twiddle equal to u of x for x in support of u, and 0 for x not in the support of u. Okay, and this is a good, this is a faithful extension of our function because support u is a closed set. So since support u is closed, we can use and one of these extension theorems from analysis, such as the it's a Tietz extension theorem, which tells me that I can extend u into a function Rn, which basically agrees with u on its support, and it's 0 outside of its support, okay? So I'm going to assume that we've done this extension, and so that means that u is now a function which is defined on the whole of Rn, okay? And now let's just do the calculation, okay? So if I look at the integral over u, uxi dx. Well, this is just going to be, I can integrate, since u is 0 outside of the set u, I can just integrate this over all of Rn, since anything outside of u will just contribute 0. U of xi dx, okay? And then if I look at just the xi component of this integral, okay, so by Fubini's theorem tells me that I can basically integrate with respect to one of the variables first. I have the integral over Rn minus 1, and then the integral from negative infinity to infinity of uxi dxi, and then dx, we'll just say dx1. Okay, when I write dx here, it's a different dx than this dx. This is now the dx volume, Euclidean volume measure on Rn minus 1. Okay, so dx now, I've basically taken out one of the dx i's, okay? Okay, where this, so let me just say, this is just dx1, dx2, dxi removed, and then dxn, okay? All right, so we have this expression here. Write this integral as not an infinite integral, but now let's say a finite integral where r is chosen large enough. I'm going to choose my capital R large enough such that it exceeds the diameter of u. So essentially, I want u to be 0 at negative r and r, okay? uxi dxi dx. A ball of radius 0 centered at r is going to contain u closure. Okay, so basically I just pick r to be really, really big. We know that u is closed and bounded, so I can choose u is not closed and bounded, u closure is closed and bounded, but the point is it's bounded, so I can choose an r large enough such that this ball just completely contains u. And then I know that my function lowercase u is 0 on these boundary points, okay? So u is 0 on the boundary points. And so then I use the fundamental theorem of calculus to evaluate this integral. And this is the fundamental theorem of calculus in one variable, just the variable xi. And this is just the integral over Rn minus 1 of the function u evaluated at negative r and r dx. When I evaluate u at the boundary, since I've chosen r large enough to be outside of the support of u, this just goes to 0. Okay? So I have that the left-hand side of this formula is 0. Now let's look at the right-hand side. The right-hand side of this formula is actually even easier to see that it's 0. So integral over partial u of u vi ds. This is 0 since the support of u is contained in our open set u. This tells me that that the boundary of u is not in the support of my function lowercase u. So the boundary of u is outside of the support of my function. The boundary is outside of the support of my function. So therefore, u restricted to the boundary is 0, right? It's 0 because the support, remember the support is the set of points where the function is non-zero. So u restricted to the boundary is going to be 0 by our assumption. So this tells me that if I integrate over the boundary, the values of u multiplied by the ith component of the normal unit normal vector, well, the values of u are just 0. So this integral, this gives me this result. Okay, so this means that the integral over partial u of u times anything is 0. All right, so we've established case 1. And it turns out that in case 1, both of these, the right-hand side and the left-hand side of this theorem are just 0. Okay, so now let's look at case 2. And so case 2 is going to be when our function has support in one of these neighborhoods of the boundary, WPKs, okay? All right, so quickly, let's just recall these WPKs. We have like a piece of our boundary, partial U, okay? So U is some larger set. We've isolated a piece of the boundary. And then we have some neighborhood, WPK, on which the boundary is the graph of a C1 function G. So X is in U intersect WPK. Tells me this is all the set of X in U such that the nth coordinate xn is less than some function G of x1 through xn minus 1, where G is continuously differentiable. Okay? And so we're going to use this definition to compute this integral on the left-hand side here. Okay? So let's begin. We have the integral over U of uxi dx. Okay, well, since support of my function is contained in WPK, I only really need to consider my domain of integration to be U intersect WPK, since the integrand vanishes outside of this set. And now, as before, I'm going to extend U to Rn by basically setting it equal to 0 outside of its support, okay? So it's going to be 0 outside of its support. And so then I can extend this integral, but essentially not to Rn, as we'll see, but to a subset of Rn, namely the subset of Rn beneath the graph of G, okay? So let's write out this explicitly. We can integrate over Rn minus 1, and then let's integrate the nth variable from negative infinity to G of x1 through xn minus 1, U of xi dxn, and then dx prime, okay? This is by Fubini, okay? And then this dx prime here, I'm using dx prime to denote the volume on Rn minus 1, okay? So you can think of it as like dx1 times dx2, etc., times dxn minus 1, okay? So I've pulled out dxn by Fubini's theorem. And then, yeah, the set of integration is basically over the set U intersect WPK, so that's going to be xn values which are below the graph of the function G. And then I've extended that notion of below all the way up to negative infinity because I've extended U to the whole of Rn, okay? So now I'm left with this integral, okay? And this integral is going to have different values depending if this xi here is, this is a partial derivative with respect to xi, depending on whether or not I is equal to n, okay? So we now need to evaluate this integral in two separate cases. So if I is equal to n, okay, then let's do it above here. So if I is equal to n, then I have the integral over Rn minus 1, integral from negative infinity to G of x prime, let's say. So x prime is just the coordinates x1 through xn. Uxn dxn and then dx prime. Okay, but as before, I can use the fundamental theorem of calculus here, and the fundamental theorem of calculus in one variable, namely the variable xn, to evaluate this integral, and it's simply equal to U evaluated at the bounds. So this integral evaluates to U evaluated at the bounds negative infinity to G of x prime, and really I should say this is the limit as r goes to negative infinity for some number r. We know that for r sufficiently large in magnitude, so as r approaches negative infinity, the support of U is going to, we're gonna exit the support of U because the u is supported in a bounded set. Since u is supported in a bounded set, if I send r close enough to negative infinity, then the lower bound of this evaluation is going to be 0. However, the upper bound is not equal to 0. And remember that these bounds are evaluated with respect to xn. So this is going to evaluate to u of x prime g of x prime, okay? Or I might as well write this as u of x1 through xn minus 1, and then the xnth coordinate gets evaluated to g of x1 through xn minus 1, okay? So this is what this integral is going to evaluate to, okay? And that's by the fundamental theorem of calculus in one variable. We have the integral, let me just write I equals n at the top here, I don't want to confuse you all. So the integral over Rn minus 1 of u of x prime gx prime dx prime, okay? All right, great. So this is the result that we'll need in for the case I equals n. So now in the case that I is less than n, we're still trying to evaluate the integral xi dxn x prime here. Okay, so the idea is that I want to evaluate this integral, and I want to use the fundamental theorem of calculus, and I have a partial derivative with respect to xi. So I'd like to use Fubini and switch the order of integration to integrate with respect to xi so that I can use the fundamental theorem of calculus on the integrand. But I can't do that a priori because this bound of this inner integral depends on xi. In particular, this bound g is a function which depends on xi. And so in order to switch the bounds, we actually first need to do a change of variables, okay? So let's do a change of variables. So I'm going to set v of x prime s equal to u of x prime g of x prime plus s, okay? And this is straight out of the Wikipedia cookbook. So this is an excellent trick that's just, this entire proof can be found in Wikipedia, by the way, if you search up this theorem. And I'll put a link in the description of the video. So, okay, so we do perform this change of variables. Now, before we actually insert the change of variables into the integrand, the idea is that if I just look at the dependence on s here, okay, so I'm trying to like replace xn with this new variable s, and if I look at the dependence on s, then basically my integral is going to turn from a negative infinity to g into a negative infinity to 0 because, right, as s ranges from negative infinity to 0, then this argument s plus g of x prime will range between g of x prime and negative infinity, okay? So somehow this change of variables is trying to get rid of the dependence on g on the upper bound of the integral. Now, to do this precisely, we now need to take the derivative of v with respect to xi. So when I take the derivative of v with respect to xi, okay, then I need to use the chain rule here. Okay, so I first have the partial derivative of u with respect to xi of this expression. Okay, where essentially remember that x prime is I'll just note it down here. X prime is like x1 through xn minus 1. And so I take the derivative with respect to the xith coordinate and evaluate that. And then I need to actually add the derivative with respect to the xnth coordinate of this expression. And then by the chain rule, I need to multiply this by g of xi of x prime. Okay? All right, so this is the chain rule. Okay, and the idea is essentially the total derivative with respect to xi of u is the partial of u with respect to xi plus the partial of u with respect to xn times the partial of xn with respect to xi, okay? So this is the general idea, is that our xnth coordinate now depends on xi. So in order to take the total derivative of u with respect to xi, I need to include this term where I differentiate the xnth coordinate and apply the chain rule, okay? Now I'm left with this expression, and so if I now integrate v of xi from negative infinity to 0 in the s coordinate, v of xi, x prime s, ds, dx prime. Okay, so v of xs by definition is going to have compact support since u has compact support. Okay, so this is going to have compact support in s and x prime. And this bound is constant now. The bounds of integration are constant. So I can use Fubini's theorem to interchange the order of integration and integrate this expression with respect to xi first. So let's just do that, negative infinity to 0, integral over Rn minus 1, Vxi dx prime ds. And then this is going to reduce to the previous case 1 argument where I'm going to have an integral, I'm going to integrate with respect to xi, and the integral is going to be from negative infinity to infinity in the xi coordinate. And so by the fundamental theorem of calculus, since v has compact support, vanishes at infinity, so this integral is going to vanish just by the fundamental theorem of calculus, okay? So we have that this integral is 0 by Fubini's theorem. But then by this identity, by our change of variables law, this tells me that the integral of the right-hand side is equal to 0 if I integrate over this integration ds to dx prime, okay? So if I integrate the right-hand side with respect to ds dx prime, I'm going to get 0. Let's do that. So I have the integral over Rn minus 1, integral from 0, from negative infinity to 0, of uxi x prime g of x prime plus s ds dx prime. Hopefully y'all can see this sliver of the board. I think you can. So, okay. So we have this, the integral of the right, I just integrated the right-hand side in the same way that I integrated the left-hand side of this equality here. Now the left-hand side integrated to 0 by Fubini's theorem and then the fundamental theorem of calculus as we just discussed. So this integral is 0. Now, what does this tell me? This tells me that, well, the left-hand side of this integral, so this term here, okay, so this tells me that this term, let's see, Rn minus 1, integral from negative infinity to 0, xi prime gx prime plus s ds dx prime. So let's look at this term here. This is the first term in this expression. Now, this is precisely, okay, notice that g of x prime for a fixed x prime is constant, okay? So g of x, if I fix x prime and I only consider this inner integral with respect to s, okay? For fixed x prime, this g of x prime is a constant. And so this is just a u sub by adding a constant number, okay? So in particular, this is again by just a u substitution in one-dimensional calculus. This is going to be equal to the integral from Rn minus 1. And now I just shift the bounds of integration and my integration variable. So this is just from negative infinity to g of x prime uxi of x prime xn dxn. Okay? Wonderful. So that's precisely, remember, this is this is the integral that we're trying to evaluate here. And this is exactly the integral that we're trying to evaluate, okay? And again, just basically, this is just you can think about the integration with respect to the s variable by Fubini is somehow independent of the integration with respect to the x prime variable. So as far as we're concerned, we're looking at this integral first, and x prime is fixed. So g of x prime is just a constant. So this is just a u sub, and I can just change the boundary. Notice that here, as s varies from negative infinity to 0, here xn is going to vary from this coordinate, this entire expression here is going to vary from negative infinity to g of x prime. So there's nothing fancy going on here. This is just a linear u sub in one-dimensional calculus, okay? All right, so now we're left with this. So this term here, this term above, is precisely the integral that we wanted to evaluate. And we've just shown that it's equal to the negative of this second term, right? Because this sums to 0. So we've just shown that this is equal to the negative of the second term. Okay, so basically, the integral that we want to evaluate. Okay, and then basically, if I look at this inner integral here, the integration with respect to the s variable, by the same logic, I'm considering, by Fubini, I can consider x prime to just be a fixed number, so a fixed value. So this expression is a constant. I can pull it outside of this integral. This integral only depends on s. And again, I can just apply the u substitution back to put this, this coordinate back into the bound of the integral. Okay? So by the same kind of logic that we've already discussed, we have this is from negative infinity to g of x prime uxn of x prime xn gxi of x prime dxn dx prime. Whew, okay, so now we're here. Okay? But now, look, we can just apply the fundamental theorem of calculus and integrate with respect to xn. We now just have a derivative which depends on the xn variable, so we can actually perform the integration with respect to xn here and apply the fundamental theorem of calculus. We have this integral is going to be the negative integral over Rn minus 1. Okay, so apply the fundamental theorem of calculus. I have u evaluated the bounds. G of xi, by the way, this term is constant with respect to xn. So we can just pull this out of the integral. Okay, so it's not going to affect my integration here. And then I'm just going to integrate this. You apply the fundamental theorem of calculus and evaluate u at the bounds here. So this is going to be, it's going to evaluate to 0 at the bound of negative infinity. So all that's going to be left is u of x prime, g of x prime, and then g of xi, x prime, dx prime. Okay, now we've made some significant progress. We're pretty much we're approaching our end goal here. We've just shown two things. First of all, the integral over Rn minus 1, integral from negative infinity to g of x prime u xi dxn dx prime. So this is equal to two different cases. So it's equal to integral over Rn minus 1 u of x prime gx prime dx prime when I is equal to n. So when this partial derivative here is with respect is the partial derivative in the with respect to the xn variable, and then in the case that it's that I is not equal to n, we have this following expression: negative u x prime g of x prime g xi of x prime dx prime, okay, when I is less than n. Okay, so we have now calculated the value of the left-hand side of the integral, okay? Now instead of just showing that it's equal to the right-hand side immediately, we're actually going to proceed using a different route, following Wikipedia. We're going to actually prove part 2 using this result, okay? And so just bear with me here. We're almost done, actually. And then you'll see that this result actually gives us an easier route to just proving case 2. And then as I discussed previously, case 2 implies case 1 by just choosing a vector field which is non-zero only in one component, okay? All right, so here's the idea, is that we know that this is true for an arbitrary function u, which is c1 of u. So now we're going to let u be a vector field, okay? So let u within c1 of u closure Rn be a vector field. And then essentially I can view this formula as holding true for all of the components of u. So we can write u as some components u1 through un, where each of these are c1 functions, okay? So the components of our vector field. And so each of these c1 functions will satisfy this formula that we've proved for this specific integral on the left-hand side of this theorem, okay? So in particular, we know that the integral of the divergence of u, okay, dx over u, this is again the summation of the integrals of u, the ith coordinate of u, and then we take the xith derivative of this. That's the definition of the divergence, as I sum over from I equals 1 to n here, and then dx, and this is over u. And now we're going to plug in this formula here, okay? All right, and notice that we're still, okay, we're still working in the case that, let me just comment that we're still working in the case that we're supported in one of these open sets, these neighborhoods of the boundary. We're still working in the support of WPK, all right? But remember that 1 and 2 are like completely equivalent, so we can prove one or the other and kind of jump back and forth however we want because they're equivalent, okay? So yeah, we have this result here, and now we are going to apply this formula. And now I feel like I'm free to erase the theorem. Yeah, okay, so I should write u intersect WPK. Right, because remember we're still working under the assumption that our support is in this this local neighborhood of the boundary, okay? And now we're going to use this result to evaluate the summation. So we basically have the explicit formula for these integrals, and they're going to end up. So if I look at this summation, let's consider the summation from I equals 1 to n minus 1. The summation from I equals 1 to n minus 1, we have this result. So this is going to be the integral over Rn minus 1 of negative u x prime g of x prime and then gxi x prime dx prime, plus now the nth term of the sum, the case when xi equals n, and we're going to use this formula, plus the integral over Rn minus 1 u of x prime g of x prime dx prime. Okay, so I'm going to view this as a dot product of two vectors, and it's going to be the following dot product. So this is Rn minus 1. We have u, and yeah, this should be ui's. I apologize. Because, yeah, just my notation, the ith component of u. Okay, so we now have the vector field u dotted with some mysterious vector v dx prime, okay? Now, what is the vector v that we're dotting with? Well, v, we can see here, is just the vector which is the first n minus 1 components are just the negative partial derivatives of g with respect to xi. So that's just negative grad g of x1 through x n minus 1 here. And then the last component is just 1, right? Corresponding to this integral where I just have u times a 1 essentially here, okay? So we can see that we can just package this result as a dot product and understand the vector that we're dot producting with as the first n components are the negative grad g, again, coming from this negative sign here, and then the g of xi's. So this is component-wise negative grad g, and then the final component is just a 1, okay? All right, so now I claim that actually this is just the result that we wanted. This is actually just u dotted with v ds, okay? So let's just say this is v prime for a second, because this is actually not the unit normal, but it's close. It's in the right direction, okay? So this is actually the result that we wanted to show, which is the case 2 of our theorem, and we've proven it on these sets WPK. And recall that we've also proven the theorem already on the set U, so we've proven it on the full cover. But let me explain why we're done now, okay? Because it's not obvious why we're done. We need to understand what this ds area element is, okay? So if I view my graph of g, let's say, so this is g of x1 through xn, okay? And we need to understand, first of all, what is the outer normal to the surface? Okay, so what is the outer normal, v? And then we also need to understand what is the surface area element. So what is the surface area element ds, okay? All right, so these are the two things we need to understand. So first of all, the outer normal vector v. Okay, so the surface is the graph of the function g from x1 to xn minus 1, okay? Now, the tangent plane I know has the following vectors. First of all, if I look at the vector 1, okay, and then 0, 0, 0, these are the first n minus 1 components. And then I look at g of x1. Okay? So this vector belongs to the tangent plane of this graph of g, okay? Why does it belong to the tangent plane of the graph of g? Well, the idea is, it's actually the definition of the tangent plane, right? If I move over 1, I basically want to attach a line in the x1 direction whose slope is precisely the partial derivative of g with respect to x1. And so this vector is exactly the direction of that line. Namely, it's rise over run. So the rise is the slope of this line is rise over run. So in this case, the rise is the partial of g with respect to x1, and the run is just moving 1 in the x1 direction. So this vector belongs to the tangent plane of this graph of this surface at any point. I just need to evaluate the point you know, x prime here. Okay? All right, so this belongs to the tangent plane. And then by the same logic, there's actually a whole list of vectors which span the tangent plane. And we can write them out. So we have another vector, 0, 1, 0, all zeros, and then g of x2. And then just repeat this all the way down and move over 1 in the xn minus 1 coordinate. Okay, and so here are n minus 1 vectors that span the tangent plane to g. So we have these n minus 1 vectors which span the tangent plane to the graph of g, which is again locally the boundary of our set U. And so notice that these are linearly independent vectors. We can see that because if we consider the matrix formed by these n minus 1 vectors, that matrix is of full rank, namely because it contains an identity matrix as a submatrix, okay? So it's certainly a full rank. And we can actually identify a vector which is orthogonal to all of these vectors, okay? Now that vector which is orthogonal to all of these vectors is namely, if I take the negative grad g, so if I take negative partial g with respect to x1, or the negative partial g with respect to x n minus 1, and then I insert a 1 here, then notice that this vector is orthogonal to all of these vectors, and these vectors span tangent plane to the graph of g. This is the normal vector because it's orthogonal to the tangent plane, because it's orthogonal to a basis for the tangent plane. And so this is the outward normal vector. Okay, so we have precisely the outward normal vector in our expression that we've derived for this integral here, okay? So we're making some serious progress. Now, let's go ahead and normalize this. So, funny terminology, but let's make it a unit vector. So let's divide it by its length here. So if I go ahead and divide by the length, this is the length of the vector. I take the norm of the vector using the Pythagorean theorem, and I divide by this. Now, since I've taken the vector and divided it by its length, this right here is the outward unit normal vector. Notice that it's outward because the xn component is positive. So in this case, right, in our picture here, we want an outward vector. Remember, the set U is beneath the graph of f. So the outward normal vector is going to be positive xn direction, okay? And, okay, so we can write this, if I use the notation of the theorem, this outward unit normal vector is my nu, okay? So I can write this as the integral over Rn minus 1 of u dot nu, which is the correct direction, but then this is scaled by a factor of square root 1 plus grad g squared dx prime, okay? And yeah, so just picture dividing this quantity by its length and then multiplying by the length, so you can see that these two are equal. Or you can just insert, right, this is equal to negative grad g1 divided by this quantity, square root of 1 plus grad g squared. So when I insert this expression for nu, I see that I recover the previous line here, okay? All right, so to complete our work, to complete our proof of the theorem in the case Remember, we're still working in the case that we're in WPK, but in this case, we'll be done as long as we show that this is equal to ds, the surface element, the area of the surface element of the graph of G. So to do that, we need to understand how to calculate ds, okay? That's what I'm going to do now. Let's again draw our surface, and let's look at the parameterization Rn minus 1. So here in Rn minus 1, I can picture a small unit of area, which is dx prime. And I can picture dx prime, this unit of area, okay, as basically, think of it as the parallelogram enclosed by the frame dx1 multiplied by the vector 1, 0 all the way to 0. And then we have dxn minus 1, 1, 0. Oh, sorry. Zeros all the way up to a 1 in the nth minus 1 position, okay? So we have the first n minus 1 unit vectors, and they're all scaled by these differential units of length dxi, okay? And then this differential unit of area, surface area in Rn minus 1 is simply this dx prime, okay, that we have here. So notice that dx prime is the determinant of essentially the matrix formed by these n minus 1 vectors that form the frame, and then the normal vector, unit normal vector, which is orthogonal to the frame, given by this expression, okay? So this is just the normal vector. So when I look at this matrix, I essentially have a dx1 all the way down to dxn minus 1, and then a 1 here. And if I take the determinant of this matrix, I get the area element dx prime. And the reason for this is a general geometric fact. If I take a parallelogram where I have, let's say, v1, v2, etc., okay? So these I could have, I can only visualize in R3, so I can only do the picture at R3, but you can visualize an entire frame of vectors in Rn minus 1 here. And then I want to find the area of this surface element. Then it's equivalent to compute the volume of a parallelepiped of height 1. So if I take a vector which is orthogonal to this frame, okay, and of unit length 1, and then I just compute the volume of this entire box here, well, the volume, since this vector is orthogonal, the volume of this parallelepiped is precisely the area of the base times the height of the box. But the height of the box is 1. So the volume of this parallelepiped is actually just the area of its base, okay? So that means that I just I start with the base, which is spanned by these vectors dx1, 0 all the way through zeros, and then dx2, etc. So these are the vectors that span the base, dxn minus 1, 0. And then the final vector is going to be orthogonal to these n minus 1 vectors. Well, that's just the unit vector in the xn direction. And so now I just look at this parallelepiped spanned by these n vectors, and its volume is precisely the determinant of this matrix, okay? From linear algebra, we know that. So this is the determinant of this matrix. Well, the determinant of this matrix is just dx1 times dx2, etc., times dxn minus 1, okay? So it's the determinant of this matrix, dx1, dxn minus 1, 1, zeros, zeros, zeros everywhere else. I'll just put it like this, okay? And and this is just dx1 through dxn minus 1, okay? All right, so the idea is very clear. Now we're going to apply this idea to the surface element. So we now lift these vectors up onto the surface. Well, what are these vectors? Now we have a frame of vectors on the surface, okay? And let me just draw two of them, because I don't want to confuse you. Okay, so when I lift these vectors up to the surface, as we described before, we just have dx1, ones and zeros, and then the z component now, the height, when I lift it up to the surface, I want the tangent plane to that surface. So the height of this vector needs to be g, partial of g with respect to the x1 coordinate. And similarly, we have this same idea holds for all of the xi's, as I've already explained. Okay? And so now, now I attach to this frame the unit normal, okay? So this gives me some sort of area, or this gives me some sort of frame for my surface element ds. Now I attach the unit normal, and when I attach the unit normal and compute the determinant of the resulting matrix, what I get is the volume of this box. But this box has height 1, and the height, right, we have this orthogonality property of the normal vector. So truly the volume of this box will just be equal to the area element ds, okay? So let's attach our unit normal vector. When I attach the unit normal vector, I have the 1 over the square root of 1 plus grad g squared, and then I have negative g x1 all the way through negative g x n minus 1 and a 1 here, okay? Now I basically form a matrix out of all these vectors and take its determinant. That determinant will give me the volume of this parallelepiped. Since its height is 1, that's going to be, obviously the height is orthogonal to the area frame of this ds, then the volume of this parallelepiped is going to be equal to the area element of the surface ds. So what we're doing is we're basically attaching a small tangent plane onto the surface, onto this surface graph of G. We're attaching a small tangent plane that's formed by basically lifting a small tangent plane in Rn minus 1 onto the surface such that it's tangent to the surface, and there's going to be some area distortion, and the area distortion is precisely the determinant formed of the matrix formed by these n vectors, okay? So when we calculate this determinant, let's go ahead and do that. When I form this matrix here, what I'm going to have is that, remember that the determinant, it works, there's this certain algebra that goes into calculating the determinant, which is that if you multiply a vector by a constant, then you can pull that constant outside of the determinant, okay? So in particular, what I want to find is, what we just discussed, is that ds is going to be this dx prime, which is the dx1 times dx2 all the way down to dxn minus 1. We're going to pull out the scaling factor of the nth vector, which is 1 plus grad g squared. So these are all the scaling factors of these vectors. And then I need the determinant of the matrix. And then I have an identity here. I have a gx1 through gxn minus 1, a negative gx1, negative gxn minus 1, and then a 1 here. Okay, and then this should be the correct formula for the area element ds. Okay, so please let me know in the comments if that was unclear. This is a really key step. Okay, so now when we calculate this determinant, okay, let's calculate the determinant. Well, basically, you use the checkerboard, right? There's something called this exterior algebra, this alternating algebra that goes into these determinant calculations. where essentially you attach a plus and minus checkerboard and you compute the determinant of the cofactors. You can expand, let's expand the determinant about this final column here. So if I expand the determinant about the final column, then I'm going to have 1. This is always going to be attached to a positive sign on my checkerboard for evaluating the determinant. The cofactor here is just the identity matrix. So that's just the determinant of the identity matrix. And then I have a minus sign. Let's move up the column here. And I'm going to have a minus gxn minus 1. And now if I compute the cofactor, I'm actually going to get the matrix where I have 1s going down in the first n minus 2 entries, so an identity matrix in the first n minus 2 entries, a 0 outside here, and then I'm going to have a negative gx1, negative gxn minus 1 like this, okay? And then I can keep going down the line and computing these, or I could use induction to prove this, okay? But let's look at this term real quick. So if I look at the second term, this term is just 1. First term is 1. The second term, let's expand this cofactor matrix. I have a column of zeros here, okay? So I can just expand about this column. Now g of xn minus 1, this term is in the bottom right-hand corner, so it's automatically attached to positive sign. So I can just go ahead and take this value multiplied by the determinant of this submatrix, which is just the identity matrix. So therefore, when I evaluate the determinant of this matrix, it's just equal to negative gxn minus 1, okay? So I have negative gxn minus 1 times negative gxn minus 1. This is plus gxn minus 1 squared. And then you can use an induction argument to show that this continues to hold all the way through gx1 squared, okay? And now, what do we get? What did we just solve for? Well, I didn't fully solve it. I didn't fully prove it out, but I think it's pretty believable at this stage that this result should hold. So we get, by using an induction argument, that this determinant is just 1 plus grad g squared. Aha. So this, we can calculate the surface area element ds, which is just dx prime times 1 plus grad g quantity squared. And that is indeed the quantity in my integral, which I have claimed is ds. So therefore, I have the following result. Now, one thing I'll note, why is this, why are we done? Well, in all of these expressions, I've kind of omitted where u is being evaluated. U is being evaluated at g, so it's in particular, it's being evaluated at the boundary of WPK intersect u, okay? So this right here is ui restricted to the boundary of u intersect WPK, okay? So in particular, right, u is being evaluated at the boundary of partial u intersect WPK, and so this integral, when I only consider, if I consider the non-zero contributions to this integral in the xn minus, or in the first n minus 1 coordinates, well, that's just gonna, the non-zero contributions to this integral are just gonna contribute from this boundary of u intersect WPK, because remember, our functions vanish outside of this set, and so here, our functions don't vanish outside of u intersect WPK. Our functions vanish outside of WPK. All right. So here I'm ending up with the integral over the boundary of u intersect WPK of u dotted with v ds, okay? And so what have we shown? Again, I'm just using the fact that we can now restrict back to the contributions to the integral that are non-zero. And so what we've shown is that the integral of over u intersect wpk of this of u divergence of u dx is equal to the integral over the boundary of u intersect wpk of u dot v ds, where this is the unit normal vector, this is the area element of the boundary. Okay, and now, so that proves the theorem in this case too, where we assumed a support in WPK. So let's summarize what we have shown. In summary, we have shown first that if support of u is contained in my set, capital U, then part 1 of the theorem holds. We have also shown that if the support of U is contained in one of these WPKs, then part 2 of the theorem holds. We also showed at the start of the video that part 1 and part 2 of theorem are equivalent by a pretty straightforward calculation. 2 directly follows from 1, and 1 directly follows from 2 in a very straightforward way. Namely, 1 just proves 2 at every term of the sum, and 2 proves 1 by the specific choice of a vector field, which is non-vanishing only in a single coordinate. So we've proven these three things, and so therefore, using the partition of unity, argument, which we explained earlier on in the lecture, using the partition of unity, we've proven the theorem holds for every open set in our cover, and so we use the partition of unity to conclude that the theorem holds for you. Okay, and then one last thing that I'll mention before we end the video. So that concludes the proof of the theorem. The last thing that I'll mention is that if you didn't want to use a partition of unity, there is an alternate idea, which is that you could cut U into a bunch of boxes, okay? So if this is my set U, and here's boundary of U, consider cutting U into a bunch of boxes, like so. And these boxes are going to be of uniform spacing, so they're going to be of uniform width. Now, by compactness of this boundary of U, we can choose such a grid such that each of these boxes, which intersects the boundary of U, satisfies our condition that its intersection with the boundary of U is the graph of a C1 function, okay? And then we can use the fact that if we prove the theorem on these boxes, we can use the fact that the outward normals, if I look at the boundary of this box, which is on the interior of U, the boundary of the box which is on the interior of U has an outward normal which cancels the outward normal of the box above it, okay? So two adjacent boxes, two boxes which share a border, share a boundary, these boxes, their corresponding unit normal vectors will be in opposite directions. And so we're going to get integrals that cancel along this part of the grid. And so ultimately we're going to get a telescoping sum, and so it's going to suffice to prove the theorem on each one of these boxes. And then we'll be able to sum up over all the boxes and apply this idea that we have these cancellations along the interior boundaries of our grid. And then notice that if I sum up the divergence of a vector field over the entire grid, well, the grid has a zero measure. So I can just, that's summing up the integral of the divergence over the interior of the boxes is the same as just integrating over the entire interior of U of the divergence of the vector field, because this grid has 0 measure, so it's not going to affect the integral. And so what that tells us is that this is actually an alternate framework that one could use to prove the theorem, the Gauss-Green theorem, without using this partition of unity argument, which is a little bit technical. But it's a similar kind of setup, and this kind of idea of cutting into a grid is actually used in complex analysis very frequently. This is honestly a more common proof technique. I was kind of intrigued, and I honestly thought that the technique that we used for this proof with the partition of unity was quite beautiful. This is just an alternate idea. An exercise to the viewer, perhaps, is to try to rewrite the proof using this proof strategy technique. And also to prove explicitly, by expanding the formulas, derive the Green's formula and the corollaries that were mentioned at the beginning of the lecture, derive them explicitly. I pretty much explained how to do it, but you can just write it out on paper using all the definitions, and that will help you if you're not as familiar with these definitions or calculus in Rn. I know that for me, I'm certainly not as familiar with calculus in Rn as I am with like 2-dimensional or 3-dimensional calculus or 1-dimensional calculus. So it certainly is helpful to do exercises like that. The last thing I'll mention is that these theorems are critical, and we're going to be using them moving forward. We're going to be using them to look at the n-dimensional wave equation, okay? So our goal now is to derive a representation formula for the wave equation at n dimensions, and this Gauss-Green theorem and all of Green's formula will provide basically the tools that we need to derive the representation formula. So I'm going to credit Wikipedia for this proof. I'm going to attach the link in the bio. Thank you all for watching, and have a great day.